which is able to generate coherent text. And the next question is that, well, can I use it to do another task, right? And another task is, for instance, a bit more challenging task, say caption generation. I want to give it an image, and that image, when I give it, it starts to talk about that image, right? So you got what I want to do, right? Image of a cat, I want it to just generate some sentence which is relevant to that image, right? I don't care what is that sentence, just one sentence, right? Now, the point here is that I already have, so let me first just write down the problem. So say I have one particular image, say this is a ImageNet, for example, image, or it's not actually ImageNet, like 256 by 256, like a good high-resolution image. Now, I want to give this RGB image into one neural network, and I want the neural network to start speaking about that, right? For example, this is image of a cat, and I want it to say something like such a cute kitty, okay? I want this to come out of my neural network, right? So what is the input? The input is an RGB image, right? What is the output? Is a sequence of text, right? You do understand that a sequence of text is basically a sequence of tokens, right? That's it, right? Text is a sequence of tokens. This is what we talked right now. Now, you have the image, the sequence at the output. They sound like they are different type of nature of data, right? Different things. One of them is a tensor, RGB, very large. The other one is a sequence of vectors, right? Now, the question is that how I can start from one tensor and end up with that sequence, and that is a valid sequence, right? We want to do that. Now, what I can say here is that, well, if I ignore the image right now, I have one language model, right? And that language model is able to talk, right? But I have no control on what it says, right? I can just simply start with some start character, and it's going to start saying something which is relevant, right? But there is no reason that I tell it, right, start, and it says exactly such a nice or such a cute kitty, right? There's no reason that it says that, right? It might say any sentence, right? Now, the question here is that how I can make my neural network to speak about what I want, right? Well, maybe I can say such a cute, and then I stop, right? But at the end, again, there is no reason that it says kitty, right? It could say such a cute dog, right? Such a cute baby, right? Anything. So I want this neural network to somehow understand that there should be something about a cat inside the sentence, right? Also the fact that that cat is a nice, right? Because image is about a nice cat, right? So these facts, these contexts should be provided to my language model. What do you think? Do you have any suggestion? How can I present that? In language or in the way of neural networks, how can I give this context to a neural network? What should I do? I have my image, right? What should I get out of the image and give it to neural network? Yeah. The features, right? A bunch of numbers, right? A vector representation of the image, right? How can I do it? I can give my cat image into a neural network. That neural network starts to process it. It's going to end up with a bunch of features, right? In chapter 4, we used to get those features and give it to one classifier, one fully connected layer, to just classify the image. Is it cat or dog, right? Now I don't need to classify anymore. I want to get these features which are representing the fact that there is a cat inside image and the cat is in a very nice situation. I want to get these concepts and give it to my neural network, right? So one thing that I can do, I can start here, right, at the initial hidden state, right, and give the initial hidden state to be something related to my image, right, the features of my image. Now, if everything works perfect, then those features are going to contain the information, enough information about the image. And it's going to tell my neural network, OK, start to talk, but keep in mind the thing that I gave you had these features, right? then this guy is supposed to start giving words which are related to that image, right? As well. Everybody sees that? Questions? Yes? Right.
So, which makes likely that not fit into other kind of pictures,
Right.
right? So
Yeah. Right. Right. Yeah. And if I wanted to talk about dog, I can just put it like again. I extract the features which are about dog, and hopefully it's gonna understand this is about dog, and then it starts to talk about the dog, right?
The same model with the same parameters, but
right. Only the features are changing. Now, the question for you might be that how it's going to start seed out of the features. Well, you do the training, right? You're going to give it one image of a cat, and then you write down the caption you want, right? And you also give it an image of a dog. You write the caption, and so on, right? Lots of images with valid captions, right? And you train it. Once you train it, it somehow figures out how it can somehow make this feature here so that this is interpreted to the corresponding sentence, right?
Oh, so the feature extraction is actually within the model.
Definitely. I'm gonna show it. Yeah, you're gonna train it end to end, from very beginning to the end, right? No, then how it can no. Yeah. You use another neural network, but you train the whole thing. Like you look at look at the whole architecture from very beginning where the image goes in to the very last sentence in the sequence, right? As a token in the sequence. You're gonna look at everything as one giant model, right? And you train everything together. All the ways everything are getting trained together, right?
So feature extraction is within, like, throughout the model.
Right. If you don't do that, then there is no reason that this guy understands those features are talking about the cat. I mean, definitely those features are talking about the cat, but they are like it's like somebody speaks in another language to this other neural network, right? It doesn't understand. Yeah.
Do you fix the gate so that it doesn't lose the feature you gave it?
Sorry, fix what?
Do you control the gate so that the image feature doesn't lose?
Yeah, you're gonna do the gates here, right? Inside your RNN, but we're gonna get rid of gates shortly. So I mean, if you really want to do it by LSTM, for example, yes, you need to have the gates definitely, and those gates are somehow try to avoid what you say. The short memory, right? This is going to happen. Nowadays, we usually do it by transformer, but of course, when you are just generating words by words, then your memory is going to carry the information about those words as well, right? And then somehow at some point, when it started to say the sentence, there are no new tokens that, I mean, you don't care if even it forgets that it's talking about a cat, right? If it says like, such a cute kitty inside a park, and yeah, you don't care what is the rest, right? It has done the job, right? And it can just add up a bunch of words after it, right? Make sense? Okay. Questions? Everybody's cool? Now, how can I generate those features? I guess we already mentioned, right? If we want to generate those features, we can put one neural network here, right? So I can get a bunch of, for example, convolutional layers, right? I get my cat image inside, then it's going to compute features after features, right? And then at some point, I have the feeling, okay, these features are enough for my language model to start speaking about a cat, right? Then I flatten them. It's going to be a vector, right? And I treat it as the initial hidden state, right? I give it to my neural network. The neural network going to look at that hidden state, the first token, right? Generates the next token and carry memory, right? Again, it's going to look at the memory, generate the next token, and so on, right? Every time the memory is carrying this information that, well, you're talking about a cat. Secondly, you have set up to this point these tokens, right? And just decide what is the next token, right? Yeah. Yes, I'm going to mention it.
Is it working with the separate?
No, it wouldn't work separately, definitely. Because how does this guy here, the RNN, would understand that the features you are giving should be interpreted as a catch, right? It only understands when it just gets trained with that, right? So that it may, it's like, as I said, like that guy is talking in one language, this guy is talking in another language. You need to train them together to make it the same language, right? Yes, I'm going to show it. Yeah, you start from very end, you backpropagate over time, you backpropagate over this guy, then you update all the weights, right? And you keep on going like that. Questions? Now, when you do this, this is what we call it encoding-decoding architecture, right? You have one encoder. The CNN here is the encoder, right? Image goes inside it. It's going to get encoded into a bunch of features, right? What are those features? Those features are the ones talking, like the output of, for example, last convolutional layer, right? This is the one which is going to go inside your RNN, right? So it's going to get the image, it's going to encode it into a bunch of features which are understandable for your RNN, and then your RNN is start from that one, and it's going to generate tokens, right? What it does, it's going to generate tokens which are somehow related to this image, so they are talking about the same data, right? But they are in a different nature, right? One of them is image, the other one is text, right? What we call the RNN, we call the RNN decoder, because it starts from encoded information about your image, right? And then from that encoded information, it starts to decode the information into the target kind of data that you want, which is a sequence of text. Yes?
It's like true learning that it understands how to interpret the extracted feature.
Yes. So you're going to train everything all together, and then when you train, this guy, the encoder, is going to learn how to set the weights so that the features are going to be useful for the decoder, and also the decoder is going to understand how it should interpret those features into tokens, right? Yeah. Questions? So now, one thing that you can say is that even what you do with the basic neural network is again encoding, decoding, right? You get the image, right? You just process it up to some features, right? And then you get the last features you classify, right? So you get your image, you encode it into something that is understandable for your classifier, and then the classifier is going to decode it into the class, right? But it's so simple that you don't call it really encoding, decoding, right? Usually when you say encoding, decoding, you are just doing somehow multimodal, right? You start from one mode, which is, for example, image, video, or something. You want to transform it into another mode, right? And there, encoding and decoding makes more sense because they are different things, but talking about the same concept, right? And then you need to make a kind of common features, which is transferable from one domain to another, right? And this is why you do it by encoding, decoding. Then this was, the term was coined by the people who started with the seg-to-seg models, like the famous paper, I'm going to put it on the course page, and then they say, oh, well, you can't transform from any kind of data to another kind of data. Pretty much you can do any task by making one encoder which is suitable for the input data and one decoder which is suitable for the output data, okay? So encoding, decoding, or encoder-decoder architecture, that is an architecture which has one encoder, and the encoder basically gets the input sequence. I call it sequence because anything that you have is a sequence. Even image of a cat is a sequence of size 1, right, of length 1. And then this is going to get one sequence as an input. The sequence could be as simple as one image, or it could be one complete text. And then it's going to just get a bunch of features at the output, so it encodes it, right? An encoded representation of the features inside the input. And then you're going to have a decoder. A decoder starts from those features, and you're going to decode it into another sequence, right? And this output sequence and input sequence could be totally different things, right? So this is going to give you a high flexibility. So you can use any encoder, you can use any decoder, and the choice obviously depends on your application, right? So, for example, here CNN made sense because I had a very giant input image, right? It was quite high resolution, so probably it's gonna make sense to use CNN, but I could replace it by ResNet, right? Maybe my image is even more complicated. I need better features. Maybe ResNet gives me better features. I don't know, yeah? I can start with the ResNet. I can cut it wherever I want, right? And then I would say the output of that layer of the ResNet are the features, right? I give it to my decoder, and the decoder starts to talk about the image. Maybe you have MNIST image, you put one MLP, right? And the MLP still is just generating useful features for you to do the decoding, yes?
I remember, one's called Vision Transformer, the VIP.
Yes, yes.
Is the one of the encoder for this?
You can do that with Vision Transformer. So once we learn Transformer, you're going to get the idea what is that guy as well. But Vision Transformer basically, you can treat any visual data as a sequence as well, right? So you don't need to get the visual data and process it all as a whole. So you get your image and you break it into patches, right? And then you would say this is a sequence of patches, and these patches are related, right? Because one part of the image is relating to another part, right? Now, you have a sequence, not one image, a sequence of patches. Your image is going to break down into a sequence of patches. And then you want to do some processing on this sequence, right? No, you can do it by RNN, basic one. You can do it by a transformer, right? When you do it by a transformer, they call it Vision Transformer, right? But at the end of the day, you can do the same, right? You can get your image, you give it to a Vision Transformer. The Vision Transformer is going to break it into patches. It's going to extract a sequence of features, right? And then you give those sequence of features to your decoder, right? Here, your decoder is the simple RNN. But if you want to work with that one, probably you want, as a decoder, you want to also use a transformer, right? The transformer is going to get the whole processed sequence, and you're going to transform it into one sequence, which is the text you want, right? So that is a kind of more advanced version of the same architecture, right? Yeah, where you are somehow using transformer as encoder and decoder both, right? And this is the one which you use nowadays in practice, right? Questions? No question? Okay, so one thing, this part, just to give you a bit of idea about how you can think about everything statistically. And the point is that, like, when you are doing deep learning, there are two different approaches to, or machine learning in general, there are two different interpretations or schools of doing things, right? One school is computational learning, which is what we do in this course. And the other version is statistical learning, which is probably the one some of you get in ECE 1513. So what is the idea in a statistical one? They do not think of what you're doing in terms of computation. There is no function in between that you are trying to estimate or approximate. The thing that you want to do, you want to generate information, and you want the information you are generating be as related as possible to the input that you have, right? And it does not mean that you are doing something different. You are again using the same neural network. The only thing is that you're going to interpret the whole process a bit differently, statistically. Now, sometimes, especially when you get into generative AI, you cannot run away from the fact that everything is working based on this statistical point of view. All ideas is working based on a statistical point of view, but when you want to implement that, you need to use computational models, meaning that you need to use neural networks to somehow realize those ideas, right? But in statistical learning, you don't really care about how you realize them. You simply think about how you can do that, right? So it's a bit of higher level way of thinking about machine learning. Now, that one somehow explains why, for example, this encoding and decoding work, because in statistical point of view, what you think about the whole model is usually one conditional distribution. What do I mean by that? For example, if I have X to be my image, right, and I want to classify it, I'm going to give X into a neural network, right? Now, up to this point, we always talked about this fact that what is inside the neural network, right? How does it process it? And every time that I want to explain it to you, I'm going to tell you, okay, this convolution is actually operating like that. There are not some numbers coming out, right? You activate them. You need to activate them properly so that you have gradients, right? And so on. This is the computational way of thinking, right? Because why we speak like that? Because we think there is one function between our image and its class, and we are trying to approximate it, right? And we want to design this approximator, the neural network in between, in the best way possible so that it can get trained properly, right? It gives us a good approximation. But one other way of thinking about this is that, well, we do know how neural networks get trained, right? So, sorry, let's forget about it. And let's say that I have this neural network. The image goes in, right? And then something comes out, right? What is coming out when I am doing classification? If I am doing MNIST classification, what is the output of the neural network? Probabilities, right? It's a probability of size 10, which is giving me the chance of every single class, right? Chance of every single class for what? Given what? Given the input, right? So what I can say that the output is actually computing the chance of the probability of every label conditioned to the input that it got, right? So this whole neural network, which could be as simple as a very shallow MLP, or it could be as large as a very deep resonant, right? At the end of the day, this whole thing is just one probability distribution, right? And that is a conditional distribution. The input goes in, the output comes out, right? Your language model even is a conditional distribution, right? A part of sentence comes in, right? The rest of it comes out, right? So the rest of sentence is the probability of the next tokens given the tokens that you have spoken up to this point, right? And then you can think of the whole process as a statistical thing, right? You would say, well, there is some computational guys, which are basically what we did up to this point in this course, who know how to train neural networks. Now let's say what we can do with these neural networks, right? And then if you think like this, encoding decoding makes more sense to you. Because basically what you are doing with RNN, again, you are doing the same thing. Every time you're going to get one input, and you're going to get some memory, hidden state. And the thing that you are generating is the probability of what is the label, for example, given what I have seen up to this point, right? Now, this memory here is depending on everything that has been seen before, right? And this means that this guy that is coming at the output is just taking one sample corresponding to the probability of the tokens coming out given whatever it has seen before, right? Now this makes sense, right? If I can build the training in a way that everything works perfectly, then this is feasible, right? And this is the way people start to think when they think statistically. If you want to just get into advanced topics, like into, for example, generative AI, this way of thinking is also needed, right? But as I said, this is not the focus of this course, because here we want to just understand how we can do it, right? And now what we can do with that is a bit more advanced, which we can do in other courses. So key point, so what you do here again, you're just sampling one output. You're just computing the chance of the token. What is the next token, given what I have seen up to this point and my new input, right? Now, if I am at the very first time step, this is something related to my image, right? And what I am, and this is a start, right? So it is, what is the chance of the first token? What is the chance of the first word, given that I have seen a cat image and I want to start my sentence? Then, well, it should be something that starts a sentence about a cat, right? And then the next time you're going to say that, okay, what is the chance of the next token, given that I have seen a cat image and the first word that I said was such, right? What is that, right? Then you're going to get the next one, A, right? A is going to happen with higher chance, right? The other tokens are happening with less chance. And most probably you're going to get A as the output, right? And then you put A as the input, then the next time you would say, I have seen a cat image, I have said up to this point such A, what is the chance of next token? No, the chances are narrowing down, right? Gradually it's going to narrow down, up to a point that like the only thing left is the chance of having end of sentence, right? there is no much chance to just continue talking, right? And this is the point where the language model stops, right? So this is what is happening somehow statistically, but you do understand that these ideas are being implemented computationally, right? At the end of the day, this probability is a neural network. And every process like making it to behave like that is happening by just doing backpropagation, computing gradients, and updating the weights, right? But you can think in a very high level that this is what is happening inside your model. Now, this is the way that is happening. So your image is going in, and then it starts to just sample something based on that image. So we're going to say, what is the chance of the first word given that I have seen an image? And you're going to keep on generating the sentence, right? Now, yeah. So now, everybody's clear about this idea, what it means, to why this decoder is really generating something about the image? You get the idea, right? And since you are now you have a good understanding about how you can train a model, how you can build a model, and things like that. Now, the next thing you can build in your mind is this way of thinking, at least for basic tasks, right? Because it's going to give you a high flexibility. Like if you want to build a new thing, if you think like that, then you would say, OK, I need an encoder here. I need one maybe transformer here. I need one, I don't know, extra decoder here, right? And then this supposedly should work, right? And now how can I do it? I'm going to put a bunch of neural networks, right? And I connect them correctly, and I leave it trained, right? And it's going to get trained. If you do the connections, everything is correctly designed, then it should work if you have enough computation and if there is no bug inside your way of thinking, right? OK, now, as I told you, if you want to train this guy, you basically train it end to end. So what does it mean? It means that you're going to go ahead and collect a data set. You're going to get a bunch of images, right? And for every image, you could have one caption. You can have multiple captions, right? You can put the cat image and just write as much relevant caption as you want, right? Every pair of cat image and a caption is one data sample, right? And then the thing that you do, this is what you get. So you get your images, you get your sample captions. And then the next thing that you do, you're going to, for example, tokenize your text, right? Of course, because you want to just feed it into a neural network. And, well, you're going to build your encoder in a way that it's going to look at the image, and then it's going to give you a feature which is matching the size of the hidden state, right? For example, if you have one LSTM whose hidden state is of size 100, the number of features that you get out of the last layer of your encoder is supposed to be 100, right? And then you give this 100-dimensional vector into your decoder, right? That's it. And then maybe you add token start, you add token end of sentence, things like that, and then you start to just pass forward everything, right? You put one image, that image goes through this, the CNN. The CNN had been just initialized by some random weights, right? It just goes through that. It's going to give you one vector of features, right? You give this vector of features to your RNN, you feed a start, right? You see the output, right? You compute the loss between that output and the first word in the caption, right? Then you're going to get the hidden state. Again, you feed it back to the same neural network, right? The next token goes in. And then you see the output. You compute the loss between the output and the second token in your caption, right? You continue doing it till you are over with your caption, right? This is one sample, right? Then you're going to do a mini batch of samples. You get a mini batch of images and captions. For every single of them, you compute that. Now you have sample losses. You just do backpropagation on the network, right? You start from your very last token. You backpropagate through time on your decoder. And then once you finish backpropagating, you got here. You're going to have a gradient. You're going to pass it backward again, right? So let's take a look here. So what you do, as I told you, you give your image. You're going to get every single token at the output. You compute the difference between your output, the loss between your output and the corresponding reference token, right? This is going to give you a loss, right? This is a sample loss. You have the sample loss. Now you're going to backpropagate. And when you backpropagate, you start with the last word inside your token, right? You backpropagate through time. You get up to this point, right? You get up to this point, right? And then here, you're going to get the gradient of your loss with respect to your hidden feature, right? Now, what is hidden feature? The gradient of your loss with respect to features that you computed. This is the gradient of the loss with respect to the output of your encoder, right? And you again backpropagate through your encoder, right? Till you get to the very input, which is your image. Now you stop. You have gradient of all the weights inside your neural network, right? You can update. And you keep on going like that, right? Everybody's clear? So you can see how the training is going on, right? OK, cool. So, yeah, any question? Yes?
So here, it means we have a caption.
We have a caption, right?
Train.
Right.
So I guess, how do we choose the caption?
This is your choice then, right? Yeah. I mean, usually for these kind of tasks, one big part of the project is to just refine your text, your data, right? So building a good corpus is a big thing nowadays. Those language model owners, they do not even share what kind of data they are using. So you just guess that they are using the whole internet and so on and so forth, but you don't really know what they are doing. And they say this is because of privacy. A part of it because of competition, right? So yeah, making data is a quite big thing. Like for language models, is a nightmare to just build a good data set, right? Yes.
You mentioned that the output of CNN should match the dimension of the
Hidden state, right?
But the thing is, the CNN output is a picture memory.
You mean it's a tensor, right?
Yeah.
But you can't flatten it, right?
Yeah, but then the right part aren't probably you need a big language model maybe.
Yes.
So this memory probably doesn't match.
It could be. This is why we use transformers nowadays. But in this particular task, if you want to just talk about one short sentence about a cat, it's enough to do it by LSTM. You can try it. And it's going to work. Because it does not really to know too much features about your image, right? Just to get the idea there is a cat here, right? If your data set is not too big, so the options that the language model has is just to talk about a few animals, for example, then it can do it. Yeah. But if you are right, if you have a very rich image and you want your language model to talk about anything, right, inside that, something that you imagine like what GPT does nowadays, right? Then of course you cannot do it by RNN. You need to do transformer. And then the transformer itself is a giant network, which has lots of ways which is able to.
So my point is there's a dimension convert from CNN to.
Definitely, yes. Definitely. I mean, you can get whatever feature you have here, and then you add one layer, which is getting that giant feature, and break it down, like reduce it in dimension. You can do that. You can do PCA here, for example, if you know what is that. Principal component analysis to get the principal components out, and then you give that one. You can do all of that. But as I said, in practice, you're going to put probably here a transformer here, and you don't need to care about that anymore. No. Yes? Sorry? Right. We do it, especially when we train a language model. I haven't talked about it here because it's a bit more detailed, but that's correct. You usually, because you don't want your if you have done a bad classification here, you don't want the language model to somehow propagate that error here, right? So you're going to give it in the training that, well, the right token is such, right? Yeah. Right, yeah. It can somehow make your training faster, but it makes the model a bit biased towards your data set. Makes sense, right? Questions? No question? Okay, cool. So yeah, if you want to do inference, again, you do the same thing. You're going to give your image as input, and then you're going to leave your language model to talk, right? And the language model starts from nothing, and then it gives you one sentence. If the training has gone well, it's going to talk about the same thing that is inside the text, right? So it's going to give you a coherent text, which is somehow depending on this image, right?